Hi guys, it's Miss Griffin. We're looking at Unit 6, Skill 4. So this question here for your essential question is a little bit loaded, but it's because there's a lot to talk about here. However, it is kind of a review of what we've done, plus some new information like talking about turning points, local and absolute maximum and minimums, and then also the least degree of a polynomial. I know this is really messy, but that says the least degree of a polynomial. So this says complete the reading below, highlight and annotate any important information you find. So I want you to pause your video at this point and read and highlight. And then hit play when you're ready to see some of that key information pointed out to you. So in this section here, we're talking about how graphs change directions from increasing and then they change to decreasing. Those are called turning points. So these spots here where we turn from increasing down to decreasing are turning points, and we refer to them as peaks and valleys. And for example, this graph has 2 valleys and 1 peak, so therefore it has 3 turning points on this graph. The next part says, how does the degree of a function determine the possible number of turning points? So if you recall, an even degree polynomial has a minimum of 1 turning point and then a maximum of n minus 1. And remember that n is just the degree of the polynomial. Because remember, an even degree would either be something like this or something like this, and it has to have at minimum 1 turning point. Right here it turns from increasing down to decreasing. And at maximum, n minus 1. So we've got this little quick example here that demonstrates how these are applied for an even degree polynomial. So we have this little example here that has a degree of 4, because the highest power there is 4, and it says that the minimum number of turning points would be 1. So we've got this first example where it only has the 1 turning point, which changes from decreasing up to increasing. So there's 1 turning point. And then we've got this one here that has 3 turning points, still again a power or a degree of 4 here. There's 1, 2, 3 turning points. And then if we talk about odd degree polynomials, an odd degree polynomial can have a minimum of 0 turning points and then a maximum again of n minus 1 turning points. And we have another quick example for that. And again, remember n is just the degree of the polynomial. So when we look at this example, this one has the power of 3 as the highest exponent, so this is degree 3. And when I look at this first one, notice it's not ever changing from increasing to decreasing. The entire time it's going upwards. So there's 0 turning points on this one. Whereas this example has 1, 2 turning points. It goes decreasing, increasing, decreasing. So again, 1, 2 turning points. And remember that it can have a maximum of n minus 1. So if the degree is 3, that's your n, 3 take away 1 is the highest 2 turning points in this particular polynomial that has a degree of 3. On this next page, we're talking about determining the least possible degree of the function. And so with this, you can never tell exactly what the degree is without more information, but we can talk about the least possible degree based on the number of turning points. It tells us that we need to first check the end behavior. This graph has opposite directions, so we know it must be an odd polynomial. So again, it's because opposite directions is odd. So it has to be a degree like 3, 5, or 7. But then when we count the number of turning points, so that's, remember, a hill or a valley, there's 1, 2, 3, 4 turning points. And remember that we know that there are 4 turning points, so there's no way it could be a 3rd degree polynomial because we have to add 1. And if we add 1, this gives us the fact that it's at least a 5th degree polynomial. It could be a 7th degree, but we would have to find out if there's more information to help us determine that. For this next part, we're talking about special turning points, and those special turning points are things that are called absolute and local or relative maximum and minimum. So absolute can also be referred to as global. You'll see that less often though. You'll mostly see absolute. And then of course we have local or relative maximum and minimums. An absolute maximum or minimum is the max or min over the entire function. So it's like the highest and the lowest. So you're going to write that in, the highest and the lowest. So when we look down here, the absolute highest point is here, and then there's no absolute minimum because these continue to go downwards forever. Okay, and then the next section we have talking about local maximums and minimums, and again, those could be also called relative. And these are various turning points that are not the highest or lowest, but they are turning points that represent a max or min for a small portion of the graph. So I just refer to these as a high point or a low point. And so for these pictures here, we have a relative or local max or minimum, because it's a low point, but it's not the lowest, because remember there was no lowest point ever because it goes to negative infinity. And this is a relative or, again, local maximum because it's a high point, but not the highest. And you can see that on the other picture as well. And then notice here that it goes on to say that even functions will have an absolute maximum or minimum, but they can't have both. And then they might have other local or relative max and mins, while an odd degree will never have an absolute minimum or maximum. And the reason for that is because, remember, odd goes in opposite directions. So there can be no highest or lowest point overall because it goes to positive infinity and negative infinity here. Okay, so that's the example of why odd will never have an absolute max or min, only local. Okay, let's flip it over. So we're just kind of recapping here, and then we're going to see a couple examples, and we're going to use the calculator to help us factor. Okay, so we've got the number of turning points on this polynomial that has a degree of n. So an even degree must have a minimum of 1, maximum of n minus 1. And remember that even looks something like this or like this. It could have 1 turning point at minimum and a maximum of n minus 1. Whereas an odd degree shoots off in opposite directions no matter how many times it changes from increasing to decreasing. But it has to have a minimum of 0 because it doesn't have to have any turning points, and then, of course, maximum, again, of n minus 1. And then what we just talked about with absolute, max, and min, this is the highest and the lowest. Point on the graph. And then relative or local is just a high or a low. But not the highest or lowest. Okay, so the next thing we're going to talk about here is this little example. It says, write each of the following in factored form, then sketch the graph, label your absolute and local max and min where appropriate. So we'll notice here that this is a degree of 3, because again the highest power is 3. And so what we're going to do is draw a little sketch. And to make this sketch, what we're going to do is type this equation into the calculator. So first step is type into the calculator. And then the second step is to find what we're going to call the zeros. Those are your x-intercepts, remember? And then third step will be to talk about bounces versus crosses, taking us back to 6.1, 2, and 3. And then fourth step will be to write the equation in factored form. Okay, so what we're going to do first is to type it into the calculator. There's a lot of stuff in my calculator, so I'm actually going to go back and make a new document, not save the changes, and we want to add a graph. And if this F1 doesn't initially pop up for you, all you have to do is hit the tab button right here, and it will pop up then. Sorry about the glare on here, unfortunately I can't get rid of those lights. So we've got F1 is that equation x to the third, and then minus 5x squared, minus x, and then plus 5. So you guys should be okay with typing this equation in originally. And I see that it's plotted here, and then what I want to do is find the zeros. That was our second step. So find these spots where it crosses the x-axis. Okay, so that's just by going to Menu, Analyze, Choice 6, and then 1 for 0, just like you would have found intersection points back in another unit. So we go for the lower bound on the left, upper bound towards the right. I click as soon as I see that little yellow thing with the word 0 pop up. And then I'm going to do that a second and it looks like a third time because I see 1, 2, 3 total spots. So Menu 6 and then Choice 1, left side, right side, Menu 6, 1, left side, right side. Now I see all of the points on there, but they're like overlapping one another. It looks kind of crazy. So all I'm doing right now is scrolling. You can see with my thumb moving the cursor around, and I notice that the hand is open right now. So what I'm going to do is push on this spot that shows the yellow hand on my calculator in the middle of the cursor and hold until it closes the hand to grab and drag this point. It just allows me to see things a little bit more clearly, so I'm going to do the same thing here. Click and hold, and then swipe to drag. It's not moving the point, it's just moving the coordinates so that I can see a little bit more clearly. Okay, so take this image in and we're going to sketch that. Notice that this would go way down and dip, come back up. So there's going to be a local or relative minimum here because it's a turning point, and then it's going to shoot back up to infinity. Okay, so we're going to sketch this. We're going to put the labels on there for the intercepts, and then we're going to continue with the rest of the problem, not using our graphing calculator. Okay? So our little sketch will look something like this, where we have the graph go here, and like I said, a turning point down on that right side. And we noticed that we had intersections at these spots. Those zeros were located at -1, +1, and 5. You don't have to write the actual coordinates, but we can just write x equals -1, x equals +1, and x equals 5. And then we're going to talk about crossing versus bouncing, and also talk about end behavior. So the ends are shooting off in opposite directions. So the opposite directions, of course, tell us that it's a third or an odd degree polynomial. And then I notice that right here it's crossing, right here it's crossing, and right here it's crossing. So these will all be odd powers. Because remember, a cross means odd power, bounce means even. So cross is odd, bounce is even. And these are powers on the factors. So to write this equation in factored form, actually before we do that I just realized we still need to label the local and absolute maximum and min. And so we talked about this one already. It's a relative or local minimum because it's a low point, not the lowest point. And then there's another turning point up here, and that's going to be a relative maximum because, again, this graph continues to go up forever. So to write this in factored form, what we're going to do is first f of x equals, because we're trying to write this equation in factored form. That's our whole purpose for doing this. We were asked to essentially factor this, and we didn't know how, so we used the calculator. Okay, and so what we're going to do here is look and say, okay, this is x equals -1, and I remember if I have parentheses to start, I would still have the x and a 1, but the sign switches, because if you recall from doing factoring, you t-chart and then you say x equals the opposite, so x minus 4 would give us x equals +4. The sign switches. So the same rule applies. Now we're going inside the parentheses, so the sign switches. And we said that they all have to be odd powers, so we'll get to that in a second. This one we know is going to give us x minus 1, and this one would give us x minus 5, because again, we're switching the signs. Then we have to go back and talk about the powers. We said that they're all odd, and it's a degree of 3. Well, there are 3 factors, so each power would be a power of 1. And again, that's because it just crossed it in a linear fashion. If it crossed it twisty through a point, then this would be a power of 3. And again, this is all just review from the previous couple of skills. All right, so we're going to see another example. I'm going to skip the calculator part with you, but I'm going to show you again the little sketch here. We're going to pretend that we all type this into the calculator at the same time. And the sketch looks as follows. Oops, don't dip down there. And this should actually be hitting the axis just one time, right there. Okay, so this is a sketch from the calculator, and we're going to pretend that I have already gone through and found the zeros. So we've got negative 1/2 by doing the same calculator steps as before, 0 and 1. And so what I'm noticing first off is that the degree here is 4. Okay, so in total we need the powers at the end to add up to 4. And then we need to talk about crosses versus bounces, and then, of course, going from the zeros to factored form. So I notice here that it's crossing in a linear fashion, so that will be a power of 1, of course. So we've got a cross at negative 1/2. We're crossing again at 0, but then at 1 we're bouncing off the axis. So that would have to be an even power. So let's just write those in real quick. This, again, of course, would be an odd power for each of those, and these would have to be even powers. So the zeros were located at x equals negative 1/2, x equals 0, and x equals 1. So we're going to translate that into factored form. So let's start with the x equals 0, because that is going to be really easy. It's just x plus 0. And then let's also talk about the x equals 1. That's going to be nice and easy, x minus 1. But it's this x equals negative 1/2 that can cause you a little bit of trouble. So what we want to do is start by thinking, okay, we have to go from here into parentheses, where it's just x plus or x minus a number. And there could be a coefficient in front of that x as well. So what we do is we just want to solve this to get the equation equal to 0 by putting it over 1. So we cross multiply. We have 2x equals negative 1. And then we want to add this 1 to both sides to get the whole equation equal to 0, because remember that when you factor, to solve, what you're doing is setting each factor equal to 0. So this is now 2x plus 1 as the factor. And another way to just think about that, again, we started with x equals negative 1/2. We know that there's division of 2, so we know our factor has to have times 2 on the x, and then this negative 1 now turns into a positive 1. Okay, so if you can think about it in that way, then you could also plug it in without having to cross multiply. But remember, we need to go back and put some powers on these. So the negative 1/2 that turned into the 2x plus 1 is an odd power of 1 because it crosses in a linear fashion. The x plus 0, again, odd power because it crosses, so it's a power of 1. And then the bounce means that we have to have an even power, so that must be a power of 2, because remember, in general or in total, this exponent of 1, 1, and 2 must total up to the degree of 4. And it does, so we have done it correctly. So this does become our answer. So again, this is a process. This process helps us to just factor something if you don't know how to factor it. And again, it helps us because we just look at the roots. Now, something I do want to point out is that in the calculator, this root actually showed up as negative 0.5 comma 0. I knew in my head that I wanted to change that decimal into a fraction, but it's important to recognize that you need to do that on your own. So you're going to change this decimal into a fraction. And so, of course, I knew that negative 0.5 was the same as negative 1/2, but if you don't know how to do it, what you're going to do is just go to your calculator and type in the calculator section. You would type in your number, and then hit menu 2, and then choice 2 is approximate fraction. To help you turn it into a fraction if you're not sure what the fraction's equivalent to in terms of the decimal. All right, flip it. We've got 2 more little things to talk about, and then you'll be on your way. So this next part is just the recap of how you identify the least possible degree. So the first step is to look at the end behavior. That phone you just heard ringing was Mr. Rogers calling me to talk about those tests that you guys just took. And then for the end behavior, we want to see if the ends are matching, then of course it's even. And if the ends are in opposite directions, then it's odd. And then the second step is to look at the number of turning points. And add 1 degree. So we'll look at 3 little quick examples and then we are done. So this first one we're looking at, the ends are in opposite directions. Okay, so it must be an odd degree polynomial. So that would be a degree of 3, 5, 7, 9, etc., etc. Then we look at the number of turning points. Remember, turning points are those hills or valleys. So we're looking here, we have 1, 2, 3, 4. So 4 turning points, TP for turning. And then we've got plus 1 gives us a 5th degree polynomial, and it's at least a 5th degree. So it could be a higher than 5th degree, but it's at least a 5th degree polynomial. On this next one, we've got ends that are going in the same direction. They're both going down, so this means it must be even. And we look at the number of turning points. I see 1, 2, 3. So again, I'm looking for those hills or valleys, those humps, or the ones that go upside down. I don't know what to call those. So we've got 3 turning points, and then we have to add 1, and so it's at least a 4th degree polynomial. So you should be a pro by the time we get to this third one. Ends are going up and down, so that's opposite directions, opposite for odd. And how many turning points? We've got 1 and 2. So 2 turning points plus 1 gives us at least a 3rd degree polynomial. All right, so again, this was sort of a recap of everything that we've done so far, plus a couple little pieces of new additional information. So go ahead and get started on your summary and then, of course, your practice problems. All right, see you later.